Case Q involves a binomial distribution. However, if you start using the binomial distribution that we learned about in 24.7, you're going to be spending hours and hours and hours trying to solve this problem. Instead, what we're going to do is approximate the binomial distribution using the normal distribution. And in that case, we're told that it works okay when n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. So when we check that to see if that's true, we take n, which is 32, times p, which is 34%, and we get 0.34 times 32 is equal to 10.88. And n times 1 minus p is 32 times 1 minus 0.34, or 32 times 0.66, and I got an answer of 21.12. So it is okay, we've checked, and this is a reasonable approximation. We're going to be approximating this problem with the normal distribution with a mean of n times p. We just calculated that. That's equal to 10.88. So on average, one can expect out of 32 people asked, 10.88 will say, or will be able to correctly report that they have A positive blood. Next, we need the standard deviation, and we're told in this part of the chapter that the standard deviation is equal to the square root of n times p times 1 minus p quantity. And when I applied that here, I got sigma is equal to square root of 7.1801, or sigma is equal to 2.67957. Better to use the extra digits in these calculations to start with and round nearer the end. Now that we have that, the biggest challenge associated with this approximation of the binomial distribution with the normal distribution is that we know the parameters of our normal distribution, but what we've got to be careful of is in the normal distribution there was nothing special or important about the lump of data at a particular whole number. But now that remember that we're approximating the binomial distribution, which is valid for only whole numbers, we have to decide, are we including the lump of the whole number or are we not? So in the first question, find the probability that at least 12 people say they do. So the average is 10.88. So in part A, we have a normal distribution that has an average of 10.88, and we're looking at about 12 and asking for the right side or the upper tail of the normal distribution. But where exactly? If we went at 12, we'd be using part of, and we made this division at 12, would be using part of the lump of 12 and not including another part of the lump at 12. But we want at least 12, which is another way of saying 12 or more. To make sure we get the entire lump at 12, we should make this point be 11.5. If we then use 11.5 and above, we would include all of the lump at 12. So that's what we're going to do first. And then the next question asks, what's the probability that fewer than 12 Well, fewer than 12 means we don't want to include any of the lump, and part B is going to have us, well, doing quite the opposite, 1 minus what we just found. I'll show you that graphically when we get to it. Let's get started on part A. So, because we want 11.5 and above, what we need to do is calculate our z here, and that means we'll start with 11.5 minus the mean, which we found to be 10.88, all divided by the standard deviation, 2.67957. I got a z of 0.2314 equals 0.2314. And now that I have that, I have to look up the formula in the z table. So we look for, hold on to something because I'm going to zoom. We don't quite have 2.34 in this part of the table, so I'll use the bottom half. So this is the bottom half, and 0.2314. Oops, it isn't in the bottom half, it's in the top half. And it's toward the bottom. 0.2314 means that the two numbers that I'm interested in are 0.23 and 0.24. And I want to go 14% of the way between 0.5910 and 0.5948, and you can apply the your favorite method of linear interpolation in order to get that there. I like to think of the fact that I want to go 14% of the way from 0.23, the answer at 0.23, to the answer at 0.24. So 14% of the way between those. When I did this, I got an answer of about 0.592, and that remembering that this is just an approximation of the binomial distribution, I'll go with the fact that I have, again I have to unzoom, so I got a z of 0.2314, I got a v of z equal to about 0.592, and 592 is not what I want, obviously, because I just want the upper tail, so I must want 1 minus 0.592, or 0.408. That was supposed to say or, but it's hard to read. So the correct answer is 0.408 for part A. Now in part B, it asks, what is the probability that fewer than 12? So I don't want the portion from 11.5 and above. I now want the portion of from 11.5 and below, and that's just this part. So for part B, I just want 0.592. And that's all of this portion right here. And we're no longer interested in the upper tail. Whoops. So everything below 11.5. And there's our answer to part B. Now in part C, it asks, what is the probability that 12 or fewer? When I'm asking about 12 or fewer, my normal distribution is still centered at 10.88 with the standard deviation equal to 2.67957. But when I say 12 or fewer, I want to include all of the lump at 12 and move to the left. That means I better go at 12, I better go at 12.5 and everything to the left of that, so that I include the entire lump at 12.5. So I want this shaded portion. Now I need to calculate my z for C. My z in this case is equal to 12.5 minus 10.88 divided by 2.67957. I got a z in this case equal to 0.58, and I get when I now look for 0.58 in the z table, it's not there. Better look in the bottom half. Nope, it must have been in the top half. There it is. 0.58 gives me an answer equal to, oops, 0.7190. So I'll go back to the problem. And phi of this z was found to be 0.719. And do I want that, or do I want 1 minus that? I include the majority of this lump now, so all of this region. So I don't want a small number, I want a pretty big number. In fact, that's my answer for part C. Notice that I don't use too many digits, or I don't use as many digits in these normal distributions as I did in, say, for example, case T. The reason I don't is because I remember that there's an approximation here of the binomial distribution, so having too many digits is just rather silly.